All right, welcome back, guys. We are going to take part two and digging into the quantum things of the world. So the first thing we looked at last time, that was what was it? Oh yeah, black body radiation. And they're like, that's crazy. How can like something just like emanate infinite energy? Because remember, if they follow Newtonian physics, the hotter something got, the shorter and shorter and shorter the wavelength got, and the shorter the wavelength, the higher the energy of your light, of your photon, the particle that carries light. And so if they did the math, it was like, they hit like an asymptote, which meant that like the distance or the wavelength got smaller and smaller and smaller, like infinitely, which meant that you could make something spit out infinite energy. Wrong. And so Max Planck, as he was trying to figure this out, remember, he just plunked in a number, and it was Planck's constant, and everything worked out. And they're like, well, what does that mean? At the time, they didn't even know. Like, nobody really knew. Nobody really knew what it meant until they sort of like had time to digest it. Now, I'm just going to give you like a moment to pause if some of this gets a little bit confusing. Some of the most brilliant minds that have ever walked the planet were really confused by this. So I'm just going to throw that out there because, it's weird. But it turns out that what that meant, that number, is that it meant that the universe is pixelated. There's like a limit, a smallest amount of energy that you could possibly have in the universe. So yeah, man, we're absolutely pixelated. But there's this other like weird thing that's going on, and it's called the photoelectric effect. And we're going to look at we're going to look at the photoelectric effect, and I want you to pay attention as to how Einstein went about solving this. So again, dude, this was Einstein's work. So, dude, if it sounds a little bit weird and you're like, what? Well, good, because it was Einstein. So, come on, give yourself a little bit of a break here. Wait, I'm gonna be still there. Okay. So look, this is called the actually, I should move over. This is called the photoelectric effect, which is a phenomenon that they knew about for like a really, really long time. But then they're like, wow, Einstein fixed it, because they couldn't quite figure out why. So here is your basic photoelectric setup. It is a glass tube, and inside there is a vacuum. So there's no air in there, and that's pretty key, because if there's air, air is actually a really, really good insulator. Like for you to scratch your feet on the carpet and then zap somebody with a little spark. There's like an amazing amount of voltage that is required for electricity to jump up across just that little teeny bit of air. So they have to make this container completely evacuated, so there's no air in there whatsoever. And what they do is they have two pieces of metal, and oddly enough, they got different results with different metal. Like this metal right here is the metal that like got hit by the light, and this is a metal that was used as like an electron receiver. And what they would do is they attached it to a small, really, really like small battery, or like a potential maker, but because they didn't want to add any current, so they try to make it as little as possible. And any change in current that was measured by the little voltmeter here, or the ammeter, that's how they knew that something was happening. So you have this all hooked up. There's your battery, and there should really be nothing going on here if you don't have a terribly powerful battery. Man, my phone is blowing up. But sure enough, here's what happened. If they exposed this to light, and it depended on what kind of light too, a photon of light would come in, smack into the metal, and out would come an electron. And how did they know that? Because every time a photon of light came in, hit that right there, and then came over to this electrode, it made a current that we picked up here. So the battery may have made a teeny weensy little bit of current, maybe. They tried to make it so it wouldn't, but there was just like a little bit of a potential, so that this was positively charged, and so when the electron came off, it was attracted to it, so that it could like measure the current. And they're like, dude, that makes no sense. Like, how does a wave do that? Because at the time, remember, everybody was thinking that light was a wave. Like, how do ripples across water make something move? And what was even weirder and crazier about this was like different frequencies of light gave these electrons different amounts of energy, which made really no sense at all, because that meant that it was like acting like a particle, and it can't act like a particle because we all know that it is a wave. You know what I mean? But this is particle-like behavior. When something comes in, bam, and knocks something else out. It's a lot like playing pool when you break the rack, right? You take the cue ball, gang, and you hit that cue ball, and it smashes everything else out all over the place. That's kind of what is happening here. A photon of light is coming in, and it's smashing out an electron. Great. That's wonderful if that photon is a particle. But everyone's saying that it's a light. Or I'm sorry, that it's a light. That it's a wave. Till Einstein, in his I think what Einstein's real genius was, not only was he really good at math, but he had an incredible imagination. And the thing that made it work for him is he allowed him to say, well, I don't know, what if? You know what I mean? And sure enough, man, that is exactly what happened here. Einstein said, well, I don't know, he said, what if? He said, what if light is a particle and it is a wave? What if it is both? Because that is some straight, trippy, sci-fi stuff. And dude, it's real. That is truly it. And at the time, man, it caused so much uproar. Woo! People got salty and bitter. There were people over here that said, oh, light is a wave. Here's our evidence. And there are people over here light is a particle. Here's our empirical, repeatable evidence. Blah, 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 blah. Boy, did people get bent. And here's Einstein going, well, I think maybe they are both. I don't know. But he did, because he's really smart. So it's not a regular particle, but it sure is. This thing called a photon, this is what carries light. And it is a particle of light. It's a particle of light. So here's the deal. Here's what we know so far. And this is, to me, one of the most mind-blowing things about light. Our light comes from the sun, right? It's coming, it washes all over Earth. Now, if we set up an experiment to measure the particle nature of photons, the light will come from the sun, it'll hit our apparatus, and it will behave like a particle. Why? Because we are asking it, or we are looking at the particle behavior. So there, it's acting like a particle, like a physical thing, okay? Right? Like bam. However, if I have the same, or not the same, if I have a, right next to that laboratory equipment, a setup to measure the wave particles of light, the same light coming from the sun will act exactly like a wave. So is light a wave or a particle? It depends on how we choose to interact with it. How did the photon know when it left the sun that it needed to act like a particle in the particle experiment, and how did it know to act like a wave in the wave experiment? And how does our interaction with the universe literally change the universe? Because it does. The way that we interact with light changes it. We put it through a particle thing, it acts like a particle. We put it through a wave thing, it acts like a wave thing, which I'm not really fully comfortable with. Wow. But anyway, here's the deal. What Einstein was able to do, and all of his other contemporaries, is he came up with this thing right here. This is the equation. So the energy of a photon is equal to Planck's constant times the frequency. Right? We already know this from last time. Planck got that. But what we got from this situation over here is that the energy of this photon is also equal to, oh, here, let me get a little pen thing going on, because I think we might need a pen. Oh, that's good. Is two things. Here we have, dude, sometimes, here we go. This right here, this is kinetic energy, right? This is the energy of motion, right? And this is what we call the work function, right? So here's how this goes. Photon comes in here, smash it here. Let me get out of the way so I don't get hit by light. Right? It comes up here. Bam! Collides with the piece of metal, and an electron comes flying off. Well, between here and here, you're going to lose energy, right? Because it takes energy to get this electron out. That requires energy. Because, if you think about it, the electrons are part of the atoms being held in there, by like the electrostatic force between the electron and all the protons in the metal. They don't just fall off, because if they did, they would. So it takes energy to remove that electron, and that is this. This is the work needed to remove the electron. Does it make sense? I hope so. And this is also different for every metal. So there's like copper, sodium, lithium, I don't know, titanium, whatever metal you want. They all have a different work function. Can you think about it? They're all like different elements, right? So they all have like different electronegativities and ionization energies and all that kind of great stuff. So if we have a photon with this much energy, right? Let's go like this. There's our energy bar, right? So if you have a photon with this much energy and this much, this is work, right? This section is work. That means this leftover here is going to be found as kinetic energy, and that'll be the kinetic energy of your electron zinging out. So the way that we can like figure this out is we have mathematical, right? We have like a math thing, equations and theory, but then we have to go into the lab and actually test it. And that's going to be what's kind of clutch. I have a little like thing that we're going to show. So that's what this equation is saying right here, okay? That's what this is saying. And we can rearrange this however we want. We have energy is Planck's constant times frequency. This is equal to kinetic energy plus the work function. So like this is the total energy of your photon. This is also the total energy of your photon, or they can just give it to you. You know what I'm saying? So so this is how we can calculate how much kinetic energy like an electron has as it comes flying out. It's just basic algebra. Does that make sense? So yeah, W is your work function. It tells you how much energy it takes to rip an electron off. How much energy is used up, right? This much, in this particular example, this much energy was used up removing that electron. And this much energy was just left over and still held in that electron, and it was used in kinetic energy. Now I'm saying kinetic energy, 1/2 mv squared. Right? Particle, like how does that... Granted, it's the energy of the electron, but like how does an electron, it's like how does it... Here's the weird thing. Let's go back to that pebble in the lake, okay? Let's say there was like a beach ball sitting, or a buoy or something sitting on like in the water, and then we threw Mike off the boat because this is fun. Those waves go like this, right? Right, they go, right, the waves are going like this. So the beach ball right next to Mike after we splash him in, or maybe a little further down where the waves are just waves, the beach ball just kind of goes up and down, right? It doesn't move. Like, you splash, you need to go like that. Like, the disturbance of the water is up and down, so the beach ball just goes up and down. So if you threw a wave at an electron, it shouldn't like pop, it shouldn't like go flying through the air. Like, the way you want that beach ball to move is if you hit it with your hand, with a physical object, to move the physical object. So it's like splashing water and then having those ripply waves like this, all of a sudden, boom, something like the beach ball goes flying out of the water. Like, what? It's not what happens, man. We've seen this a million times. Stuff in the water, it just floats, it just bobs up and down, right? It's like, if you're in that same boat, and waves come by, you get rocked around up and down. You don't get launched out of the lake. But this is what's happening here. That right there, right there. All right, I got it. That right there is equivalent to someone throwing a pebble in the water and a leaf being like knocked out of the lake, like a leaf that's floating on the water being knocked out of the lake and flying through the air. Like what the heck? This is crazy. It's crazy stuff, but it's true. Light is both. Like, it's got both. Okay, so here's what I want to do here, guys. I'm going to see if I can go... I'm going to discard my annotations. I'm going to come down here. Oh, there it is right there. Oh, do I have it right here? Boom! Look how fancy we're going to be. Look, I'm going to do like a quick little thing here, okay? So this is a simulation, so you can kind of like see sort of what happens with like kinetic energy. So what I've got here You see that? That's sodium. I can choose all kinds of different sodium, but let's stick with sodium. This is a lamp, and here's my intensity. I can see how the light gets bright, the light gets less bright. So this is shining, and there is a thin layer of sodium. This is my battery to show some kind of potential, and here's my current meter. There's my glass tube. It's all a vacuum. Yay! So what I'm going to do is I'm going to move it way up here into infrared. All right, so infrared is pretty low energy. Remember Roy G. Biv. So red energy is pretty low. The purpley energy is higher and higher energy. So we would expect that this region should not knock off too many electrons because, you know, atoms hold on to their electrons. So as we increase the energy at some point, look at that, electrons come flying off, right? So I want you to kind of pay attention a little bit. Here's 447. Do you see generally how fast these are going? Now we're going to increase the intensity. Yeah, the velocity doesn't really change a whole heck of a lot, does it? The velocity doesn't change a whole heck of a lot. Average. So let's increase the energy of the light. Now what we've done is this light beam has more energy in average. This is always going to be like outliers, right? But overall, generally what's happening is because this has more energy, the light coming out of that lamp, do you see how the electrons are going faster? Does that make sense? So the intensity of the light, all right, do you see that? Now we're going to reduce the intensity and we're going to wait a little bit. All right, so the intensity with light is not, it's not pure energy. It's like the number. So the amplitude of these waves, it's the number of photons. So if you see so what this tells us, what we know here, is if you see a very, very bright light, it's not that those photons have more energy that makes it bright. It's just that there are more photons. So this is a very low intensity. Look right here, it's very dim light. So that means there are very few photons. But we take the intensity and we crank it up really high. That means we have more photons dislodging more electrons. Do you guys get what I'm saying? So what we're going to do experimentally is you take this thing and you just keep sliding it down, sliding it down, sliding it down, sliding it, less energy, less energy, less energy, less energy. And as you notice, the less energy it has, the slower they're going. Whoa. It seems to have stopped. So 535, it's still going. At 540, it has just stopped. Do you see how the flow of electrons, it has just stopped? Why would it just stop? And the reason it just stops is because the photons at 540 nanometers just do not contain enough energy to rip off an electron. However, if we take this thing and we increase it by just 1 nanometer, well, apparently that's not enough. Nope, still haven't hit that threshold. Oh, I'm going the wrong way, aren't I? I'm making it bigger and bigger and bigger. Oh, 530. 539. Oh, no. Dude, look at that. 539. Do you see how slow these electrons are moving? That means I must be just barely at that threshold. So at 539, I can remove them with just barely enough energy left over. I increased the energy just the slightest bit, and yeah, look at that. It's like a light switch. It just stops. So somewhere between 541 and 539, that's my wavelength for sodium. And that energy is going to be like what? Let's do 539.5. That'll correlate to the energy it takes to remove an electron. So there you go. That's the photoelectric effect. It changes with every metal. It changes. So if you put platinum here, like this is going to be different for sure. Oh, there it is. Oh, platinum's way down here, right? Why? Apparently platinum holds on to its electrons a little bit better, which would make sense, really, because platinum is a beautiful solid metal, but sodium, man, remember when sodium hit water? It can barely hold on to its electrons. So you can remove it with weak green light. Yeah? Good? Does that make sense to you guys? I certainly hope so. Let's go back here. Oh, you thought that we were done, but we're not. All right, so this is pretty easy. Calculate the energy in joules of a photon with a wavelength. You know, this is the kind of thing that's going to make me go insane by the time before I retire. All right, so wavelength equals 5.00 e to the 4 nanometers. Going to convert that to meters right away. Oh, okay, so we know that energy is equal to Planck's constant times, what was it? Was it frequency? But this is wavelength. Oh, got it. Right. We also know, I'm going to write this up here, that the speed of light is equal to wavelength times frequency. So if we have wavelength and we need frequency, how are we going to do that? Like this. Frequency is equal to the speed of light divided by wavelength. Awesome. So 5, let's just get into it. 5 e to the 4. Oh, this is nanometers. And 1 nanometer is the same as 1 e to the minus 9 meters. Hold on. Get back. This is going to equal, oops, what did I get? 5 e to the minus 5, right? Sweet. So we're going to take that, we're going to pop it into like this version of this thing. So my energy, what did I write? So my energy is going to be equal to Planck's constant. Look it up. Don't memorize it. 6.63 e to the minus 3.5, I believe. 3.5. Yep. And then C, this is 3 times 10 to the 8. And my wavelength is 5 e to the minus 5. Gonna math that all out. And I got 3.98 e to the minus 21 joules, which kind of makes sense because one photon shouldn't have a whole lot of energy if they add. So there you go. All right. Now the next question. A photon, find the energy. So we're going to be basically doing the same thing where we're going to use energy is equal to Planck's constant times speed of light divided by a wavelength, right? Which is a remember, this is just an expansion of that, right? We just kind of blew it up a little bit. So a photon with a wavelength of 5 times 10 to the minus 2 nanometers. All right, so we're going to do the same exact thing. Oh, it's 5. Oh, and this is 5. Oh, look at that. And the only difference is that we have order of magnitude of 6. So I'll bet you, if everything is the same, we should only have a difference in order of magnitude. I'll bet. So this would be a nice way to double check everything. So the first thing we're going to do is we're going to convert our wavelength into, our wavelength from meters into, from nanometers into meters. See, I'm getting all flustered now. I'm all flustered. Okay. Try doing this with kids, guys. It's crazy. I don't even know what it's like. This is like 10 minutes later. So, all right. That's right. We're converting this, my nanometers, into meters. So that's 1 e to the minus 9. But we're going to use a capital for 1 nanometer. And this is meters. So it's going to get, I'm going to use my cheat sheet. Oh, shoot. I didn't write this one out. What is it, 5 to the 11? All right. I'm just going to go with it. I'm just gonna run with it. I don't even care. Let's see how it do. So that's step 1, right? The first thing I'm doing is converting nanometers to meters, and then step 2, I'm going to actually calculate the energy, which is going to be equal to Planck's constant with a 6.63 e to the minus 35, which is so small. I mean, that is just so small, times the speed of light, 3 times 10 to the 8, divided by our wavelength, 5e to the minus 11. I'm going to pause you one more time. Okay, and I got for this one 3.978 e to the minus 15. And now I need to double check. What was my first one? All right, my first one up here was to the minus 21. Here's to the minus 15. That's off by 15, 16, 17, 18, 19, 20, 20. Is off by 6. So, and this is bigger, right? So this is more energy, and this is less, which is good, because we, if the whole Roy G. Biv thing says the X-rays are supposed to have more energy than infrared. Infrared's supposed to be relatively low energy. Man, that's easy. That was great. I can do this. So can you? Oh God, there's more. Okay, so the work function of cesium metal is 3.42 times 10 to the minus 19 joules. That means it requires this much energy to pop out an electron. All right, that's easy. We can do this one. Oh, you know what? I'm a fan of the purple today. I don't know why I'm feeling purple. Okay, so we need to do two things. One is calculate the minimum frequency of light required to release electrons from the metal, and then we need to calculate the kinetic energy of the electron. Calculate the kinetic energy of the electron if light or frequency blah 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 is used for irradiating the metal. In other words, pop out an electron. All right. Let's see what we can find here. I know that I'm going to need some kind of equation that has something to do with work. What is it? Oh, wait. Here it is. Right there. E is HV is kinetic energy plus work. Very nice. Okay. And, okay. E. Okay, let's see if I can remember that one for the next couple minutes. So, E. Nice. Or kinetic energy plus work. I got that wrong. You know, guys, the rains it pours, but, we just keep on keeping on. All right, so we need to calculate the minimum frequency of light required to release the electron of the metal. All right, so the energy that we need for this electron, so we need, in this case, we need the energy to equal exactly the work function, right? And so the way that we calculate energy, in this case, frequency, we're gonna use this one. We're gonna substitute HV for our energy, right? So again, let me just go back because I'm kind of blathering a little bit. Is we need the frequency of light required to release the electron. So that means that the energy of our photon is going to have to be exactly equal to the work function. All right, so there's no leftover energy. The only thing we're looking at is just the energy to pop it off, right? The work function. And the way that we calculate energy is Planck's constant times frequency, and that is going to be equal to our work function, which is right here. Is 3.42 times 10 to the minus 19 joules. So that's going to be 6.63 times 10 to the minus 35. Right? Is that what it is? 6.63? Oh, 34. Right? Times our frequency. It's going to be equal to 3.42 e to the minus 19. My thing is acting up a little bit funny. All right, I'm going to pause you one more time. I'm going to do some math. I'll be right back. Okay, so I got 5.1. All right, doing the math here. I hope you don't mind if I pause you. I figured just make the videos go faster. I got 5.158 3, 7, whatever, e to the 14. So that'll be hertz. And so what do I got here? I got 3, 1, 2, 3, 5.16 hertz. Yeah? Yeah, that's easy. Okay, so the next one. Calculate the kinetic energy. So I'm going to need this. I'm going to need to find this here. Here, I'm going to just write this down. Energy equals kinetic energy plus work, just so I have it there. And this is also equal to HV, just so I have it. So calculate the kinetic energy. So that's what I'm looking for. Of the ejected electron, if light of frequency 1 times 10 to the 15th is used for irradiating the metal. All right. Okay, so what else do I know? I know that my work function is 3.42 times 10 to the minus 19th. All right, let's see if we have everything. We're looking for kinetic energy, right? I've got work, and the energy is Planck's constant, which I know. Plug and chug, guys. Plug and chug. Okay. So, the equation that I'm going to use is HV, Planck's constant times frequency, is equal to kinetic energy plus the work function. Which in my brain makes sense because the energy of the photon is going to be equal to, right, the energy of the photon, that's my starting energy. It'll be equal to the amount of energy used to remove the electron, and all the leftover energy will be kinetic energy. That kind of makes sense to me. Let's see it. Let's see if this actually works. All right. So H, 6.63 times 10 to the minus 34. Frequency. I love this frequency because there's no converting or anything. It's just 1 times 10 to the 15. That's going to be equal to my kinetic energy, or plus, not times, my kinetic energy plus 3.42 times 10 to the minus 19. I should really be looking at my units for this, but, you know, I'm having one of those days and I just don't feel like looking at my units. You know, don't care. All right, I'm going to go math. I'll be right back. Okay, I'm back. I made a mistake, if you can believe it, during doing my mathing, which is this mistake that everybody falls into, is this is a plus over here, guys, right? So what I initially did is I multiplied and then I divided. And I was like, you look at the numbers, it should be a really weird number. So I say that just to remind you to be careful that this is addition, not multiplication. So don't fall into the same, robot mode of just like doing without thinking, which is sort of how my day's going. How's your day going? So I got 3.21 e to the minus 19 joules. Bam! Which, if you go back to our little simulation thing that we did, remember, it's the energy of the photon, the frequency, right? Once you hit that frequency to eject it, all that extra energy is used or turned into kinetic energy. So there's that. What else do we have next, guys? Today our homeworks are going to be 714. to 722 even. All right, guys, that's you. Time out, bud. Time out. Let me just finish up with these guys. Look, all I need you guys to do for today, right, is I need you to watch this video, take down the notes, and then I need you to do the outline for section 7.2. This is the homework that is coming up. It's not going to be due until end of the day, like Friday night, Saturday morning. You know what I mean? It's due Saturday at 8 o'clock. So that if you're up past midnight, which a lot of people are, oddly enough, like amazing amount of people are up past midnight. I'm making it due at 8 o'clock so you can have all night. It should not be done on Saturday. That's insane. It's just due by 8 o'clock on Saturday, so it's done at night. So let me review the way we're doing this. Today, watch the video, take some notes, outline chapter 7.2, right? 7.2, the photoelectric effect. Upload 7, that your outline for, like, that's your assignment for today. Tomorrow will be the homework, but there's that one. Wish me luck, guys. Wish me luck.